The darkness between worlds is not empty. It is filled with time. Time measured not in hours or days, but in years that stretch across the cold geometry of orbital paths, across the slow ballet of planets, circling a single star in a galaxy that contains hundreds of billions of others. To ask how long it would take to visit every planet in our solar system is to ask a question that sounds simple but unfolds into layers of complexity that touch the very limits of human engineering, endurance, and ambition. It is a question that requires us to confront distance on a scale that defies intuition, to understand velocity not as something we feel on a highway, but as something measured against the pull of gravity wells and the conservation of momentum in a vacuum where friction does not exist. Before we can answer, we must first understand what we are truly asking. We are asking about the nature of space itself, about the machinery we have built to cross it, and about the constraints imposed by physics that cannot be negotiated or bypassed. If you're watching this, consider expanding to full screen, and if this journey through the vast mechanics of our solar neighborhood resonates with you, a subscription would allow us to continue exploring these frontiers together. Now, let us begin at the beginning with the simplest foundation: distance. The solar system is not a neighborhood in any terrestrial sense. The distance from Earth to the Moon is approximately 384,400 kilometers, a journey that took the Apollo missions roughly 3 days to complete. This is the only journey to another celestial body that human beings have physically completed. It is the baseline against which all other distances must be measured, and it is already so vast that it would take more than 9 years to walk that distance at a steady pace without stopping. Yet the Moon is practically adjacent to us when compared to the planets. Mercury, the closest planet to the Sun and the innermost world of our system, orbits at an average distance of about 57.9 million kilometers from the Sun. Earth orbits at 149.6 million kilometers, a distance we define as 1 astronomical unit, or AU, a measurement created specifically because writing out these numbers repeatedly becomes cumbersome. Venus, the second planet, orbits at roughly 0.72 AU. Mars, the fourth planet, orbits at 1.52 AU. These numbers sound clinical, but they represent gulfs that swallow human timescales whole. To reach another planet, a spacecraft cannot simply point in its direction and accelerate. Orbital mechanics, the branch of physics that governs motion in space, dictates that trajectories are curves, not straight lines. Every object in the solar system is moving, and moving fast. Earth travels around the Sun at approximately 30 kilometers per second. Mars moves at about 24 kilometers per second. A spacecraft leaving Earth does not start from rest. It begins with Earth's orbital velocity already embedded in its motion. To reach another planet, mission planners must calculate a transfer orbit, a path that intersects the orbit of the destination planet at precisely the moment the planet itself will be there. This is known as a Hohmann transfer orbit, named after the German engineer Walter Hohmann, who described it mathematically in 1925. It is the most fuel-efficient path between two circular orbits, and it is a compromise between time and energy. A Hohmann transfer to Mars, for instance, takes advantage of Earth velocity to fling the spacecraft into an elliptical orbit that stretches outward toward Mars's orbit. The spacecraft coasts along this ellipse, unpowered for most of the journey, falling and rising through the Sun's gravity well until it reaches the point where Mars will be. The timing is everything. Launch windows, the periods when Earth and Mars are aligned correctly for such a transfer, occur roughly every 26 months. If you miss the window, you must wait for the next one. The journey itself, using this minimum energy trajectory, takes approximately 6 to 9 months depending on the specific alignment and the year. This is not a fast journey. It is not a journey where you can turn around easily. Once committed to the trajectory, the spacecraft is bound to it by the laws of motion, and altering course requires expending propellant, which is a finite and precious resource. To visit every planet, then, is not a matter of simply hopping from one to the next. It is a matter of chaining together multiple transfer orbits, each requiring precise timing. each consuming months or years, and each constrained by the positions of the planets at any given time. The planets do not wait for us. They move in their orbits according to Kepler's laws, which describe how orbital period increases with distance from the Sun. Mercury completes an orbit in 88 Earth days. Venus takes 225 days. Earth takes 365.25 days. Mars takes 687 days. Jupiter, the first of the giant planets, takes 11.9 Earth years. Saturn takes 29.5 years. Uranus takes 84 years. Neptune takes 164.8 years. These periods mean that the planets drift in and out of alignment with one another in patterns that repeat over decades and centuries. A trajectory that visits multiple planets must account for these movements, and the mathematics involved becomes not just complicated but monumental. The concept of a grand tour, a single mission that visits multiple planets, emerged in the late 1960s when NASA scientists realized that a rare alignment of the outer planets would occur in the late 1970s. This alignment, which happens only once every 175 years, would allow a spacecraft to use gravity assists, also known as gravitational slingshots, to travel from Jupiter to Saturn to Uranus to Neptune without requiring enormous amounts of fuel. A gravity assist occurs when a spacecraft passes close to a planet and uses the planet's gravity to alter its trajectory and speed. The spacecraft falls toward the planet, gaining speed, then swings around it and is flung out in a new direction. From the perspective of the Sun, the spacecraft has stolen a tiny amount of the planet's orbital momentum, speeding up at the planet's expense. The planet, being vastly more massive, slows by an amount so negligible it cannot be measured, but the spacecraft can gain thousands of kilometers per hour of velocity. Voyager 2, launched in 1977, executed this grand tour. It flew past Jupiter in 1979, using the giant planet's gravity to accelerate and redirect itself towards Saturn, which it reached in 1981. From Saturn, it continued to Uranus in 1986, and finally to Neptune in 1989, 12 years after launch. This remains the only mission to have visited Uranus and Neptune. Voyager 2's trajectory was not the fastest possible path to any single one of these planets. It was a carefully threaded path that took advantage of their positions to visit all four. The mission demonstrated that visiting multiple planets in a single journey is possible, but also demonstrated the timescales involved. 12 years to reach 4 planets. And Voyager did not stop at these planets. It flew past them, spending only hours or days in close proximity before continuing on its way out of the solar system. A mission that intended to visit every planet would face far greater challenges. To understand those challenges, we must examine each planet individually, not just in terms of distance, but in terms of the orbital mechanics required to reach it, the environments encountered there, and the cumulative time required to move from one to the next. Let us begin with Mercury, the smallest planet and the one closest to the Sun. Mercury orbits at an average distance of 0.39 AU from the Sun, but reaching it is not straightforward. Because Mercury is deeper in the Sun's gravity well than Earth, a spacecraft traveling there must shed velocity, effectively falling toward the Sun. This is counterintuitive. In everyday experience, traveling towards something requires speeding up, but in orbital mechanics, moving to a lower orbit requires slowing down. A spacecraft leaving Earth must fire its engines retrograde, opposite to its direction of travel, to lower its orbit and fall inward. The first spacecraft to visit Mercury was Mariner 10, launched in 1973. It used a gravity assist from Venus to reduce its velocity and reached Mercury in 1974, approximately 5 months after launch. However, Mariner 10 did not enter orbit around Mercury. It flew past 3 times using a trajectory that allowed repeated encounters. The first spacecraft to orbit Mercury was Messenger, launched in 2004. Messenger did not travel directly to Mercury. Instead, it flew past Earth once, Venus twice, and Mercury 3 times, using each gravity assist to gradually reduce its velocity relative to the Sun. The entire journey took 6.5 years. Messenger finally entered orbit around Mercury in 2011. This duration was necessary because directly inserting into orbit around Mercury from Earth would require an enormous amount of propellant to slow down, far more than could be carried by a reasonably sized spacecraft. Why so much propellant? Because velocity is expensive in space, and changing velocity, known as delta V, is the currency of spaceflight. The rocket equation, formulated by Konstantin Tsiolkovsky in the late 19th century, describes the relationship between the mass of a spacecraft, the mass of its propellant, and the change in velocity it can achieve. The equation is exponential, meaning that small increases in required delta V demand large increases in propellant mass. To achieve high delta V, a spacecraft must carry more propellant, but carrying more propellant increases the spacecraft's mass, which in turn requires even more propellant to accelerate. This tyranny of the rocket equation is the fundamental constraint on all spaceflight. Chemical rockets, which burn fuel and oxidizer to produce thrust, have specific impulse values, a measure of efficiency, that limit how much delta V they can provide. Even the most efficient chemical rockets cannot provide enough delta V for certain missions without making the spacecraft impossibly large. This is why gravity assists are essential for missions to the outer planets and for missions that require large changes in velocity. They provide delta V without expending propellant. However, they're not free. They require time. Each gravity assist requires traveling to a planet, arriving at the correct time and position, and then waiting as the spacecraft swings around it. A mission to Mercury that uses gravity assist from Venus might take years. A mission that attempts a direct trajectory with large propellant reserves might take months, but would require a much heavier launch vehicle and spacecraft, increasing cost and complexity. The choice between time and mass is a constant trade-off in mission design. After Mercury, the next planet is Venus. Venus orbits at 0.72 AU, closer to Earth than Mars, but presenting its own difficulties. Venus has a thick atmosphere of carbon dioxide with surface pressures 90 times greater than Earth's and temperatures hot enough to melt lead. Any lander sent to Venus survives only hours before being crushed and incinerated. However, for the purpose of a flyby mission, Venus is relatively accessible. Transfer orbits to Venus from Earth take approximately 3 to 5 months using a Hohmann transfer. Numerous missions have visited Venus, including the Soviet Venera probes, NASA's Magellan orbiter, and the European Space Agency's Venus Express. These missions demonstrate that reaching Venus is achievable within a time frame comparable to reaching Mars, but the hostile environment means that extended exploration on the surface is not currently feasible. Moving outward from Earth, Mars is the next target. Mars has been the focus of extensive exploration because its environment, while harsh, is more hospitable than that of any other planet. The thin atmosphere, cold temperatures, and lack of a magnetic field present challenges, but they are challenges that robotic missions have successfully navigated and that future human missions might overcome. As previously mentioned, transfer orbits to Mars take 6 to 9 months, and launch windows occur approximately every 26 months. Multiple spacecraft have reached Mars, including orbiters, landers, and rovers. The Perseverance rover, launched in 2020, took about 7 months to reach Mars. The journey is long, but it is within the realm of what current propulsion technology can achieve reliably. Beyond Mars lies the asteroid belt, a region of space between approximately 2.2 and 3.3 AU from the Sun, filled with rocky bodies ranging in size from dust grains to Ceres, a dwarf planet nearly 1,000 kilometers in diameter. The asteroid belt is not densely packed. Spacecraft can traverse it without high risk of collision. However, visiting specific asteroids adds time and complexity. The Dawn mission, launched in 2007, visited the asteroids Vesta and Ceres using an ion propulsion system, a type of electric propulsion that provides very low thrust over long periods, allowing for high total delta V. Dawn took nearly 4 years to reach Vesta and more than 7 years to reach Ceres. Ion propulsion is more efficient than chemical propulsion in terms of specific impulse, but the low thrust means that accelerations are gradual and mission durations extend. After the asteroid belt, the scale of the solar system expands dramatically. Jupiter, the largest planet, orbits at 5.2 AU. This is more than 5 times Earth's distance from the Sun. The journey to Jupiter using a Hohmann transfer would take approximately 2.7 years, but most missions to Jupiter have used gravity assist from Venus, Earth, or both to reduce travel time and propellant requirements. The Galileo mission, launched in 1989, used gravity assist from Venus and Earth twice before reaching Jupiter in 1995, a journey of 6 years. The Juno mission, launched in 2011, used a gravity assist from Earth and reached Jupiter in 2016, taking 5 years. The travel time to Jupiter is measured not in months, but in years, and this is using optimized trajectories and powerful launch vehicles. Jupiter is immense, with a mass more than 300 times that of Earth and a powerful magnetic field that creates intense radiation belts. Any spacecraft visiting Jupiter must be hardened against radiation, and any trajectory passing close to the planet must account for the intense gravitational influence. Jupiter has dozens of moons, 4 of which, Io, Europa, Ganymede, and Callisto, are large and scientifically significant. A mission that intends to visit Jupiter and explore its moons must spend additional time in the Jovian system, potentially months or years, conducting flybys or entering orbit around the moons. The Europa Clipper mission, scheduled to launch in the 2020s, will spend several years reaching Jupiter and then several more years conducting dozens of flybys of Europa. The time required to explore a planet thoroughly is far greater than the time required simply to reach it. Beyond Jupiter lies Saturn, orbiting at 9.5 AU. A Hohmann transfer to Saturn would take approximately 6 years, but again, gravity assists are typically used. The Cassini mission, launched in 1997, used gravity assists from Venus twice, Earth, and Jupiter before reaching Saturn in 2004, a journey of nearly 7 years. Cassini then spent 13 years orbiting Saturn, studying the planet, its rings, and its moons, particularly Titan and Enceladus. The mission ended in 2017 when Cassini was deliberately crashed into Saturn's atmosphere to avoid contaminating the moons with Earth microbes. This mission illustrates a critical point. The journey to Saturn is measured in years, and the exploration of Saturn, if done properly, is measured in decades. Saturn's distance from the Sun means that solar power becomes impractical. Both Galileo and Cassini used radioisotope thermoelectric generators, or RTGs, which convert heat from decaying plutonium into electricity. RTGs provide a steady, reliable power source, but are expensive and limited in availability due to the scarcity of plutonium-238. This adds another layer of complexity and cost to missions to the outer planets. A mission visiting every planet must carry sufficient power generation capability for the entire journey, which could span decades. Uranus orbits at 19.2 AU, roughly twice Saturn's distance from the Sun. A Hohmann transfer to Uranus would take approximately 16 years. Voyager 2, using a gravity assist from Saturn, reached Uranus in 9 years from launch. No mission has returned to Uranus since Voyager 2's flyby in 1986. Uranus is tilted on its side, with an axial tilt of 98 degrees, meaning its poles point nearly directly at the Sun during parts of its orbit. This unusual orientation creates extreme seasonal variations and complex atmospheric dynamics. Uranus has a faint ring system and 27 known moons. A comprehensive mission to Uranus would require not just reaching the planet, but spending time in orbit, studying its atmosphere, magnetosphere, rings, and moons. The time required to reach Uranus alone is a significant fraction of a human lifetime. Neptune, the outermost planet, orbits at 30 AU. A Hohmann transfer would take approximately 31 years. Voyager 2, using gravity assist from Jupiter, Saturn, and Uranus, reached Neptune 12 years after launch in 1989. Neptune is a deep blue world with the fastest winds in the solar system, exceeding 2,000 kilometers per hour. It has a ring system and 14 known moons, the largest of which, Triton, is geologically active and orbits Neptune retrograde, suggesting it is a captured Kuiper belt object. Neptune's distance means that sunlight is extremely faint and temperatures plunge to cryogenic levels. Communication with a spacecraft at Neptune's distance takes more than 4 hours one way, meaning that any command sent from Earth takes 4 hours to reach the spacecraft, and any response takes another 4 hours to return. This delay makes real-time control impossible. The spacecraft must operate autonomously, following pre-programmed instructions and reacting to situations on its own. So far, we have considered the minimum travel times to each planet using optimized trajectories, gravity assists, and efficient propulsion. But visiting every planet in a single mission is not simply a matter of adding these times together. The planets move continuously, and their positions relative to one another change constantly. A trajectory that visits multiple planets must be designed to take advantage of planetary alignments, and such alignments are rare and specific. The Voyager Grand Tour was possible because of the alignment of the outer planets in the late 1970s. Such alignments do not occur frequently. A mission attempting to visit all 8 planets would need to wait for a favorable alignment or accept a much longer mission duration. Consider the problem from a mission design perspective. Suppose a spacecraft is launched from Earth with the goal of visiting, in order, Mercury, Venus, Mars, Jupiter, Saturn, Uranus, and Neptune. The spacecraft must first travel inward to Mercury, which requires reducing velocity and falling toward the Sun. One approach would be to use a gravity assist from Venus to reach Mercury, as Mariner 10 did. From Earth to Venus might take 4 months, then Venus to Mercury another few months, totaling perhaps a year to reach Mercury. After a flyby of Mercury, the spacecraft must travel back outward to Venus, which it might already encounter on a return trajectory if the timing is right. Another few months brings the total to perhaps 18 months. From Venus, the spacecraft must travel to Mars. A transfer from Venus to Mars is not commonly executed, but it would involve adjusting the orbit to match Mars's distance and velocity. This could take a year or more, depending on the alignment. After Mars, the spacecraft must travel to Jupiter, a jump from 1.52 AU to 5.2 AU. Using a Hohmann transfer from Mars to Jupiter would take approximately 2.7 years. However, the spacecraft might use a gravity assist from Earth or Venus to increase velocity, but this would add time and depend on planetary positions. Let us assume a direct transfer taking 2.7 years. The total mission time is now approximately 5 years, and the spacecraft has visited only 4 planets. From Jupiter, the spacecraft must travel to Saturn, which could take approximately 6 years using a gravity assist from Jupiter, but more likely closer to 4 years if the trajectory is optimized. The total is now 9 years. From Saturn to Uranus, using a gravity assist from Saturn, the journey could take approximately 4 years, bringing the total to 13 years. From Uranus to Neptune, using a gravity assist from Uranus, another 3 to 4 years, totaling approximately 16 to 17 years. But this calculation is overly simplified. It assumes that the planets are conveniently aligned at each stage, which they will not be. It assumes that gravity assists are available and correctly positioned, which depends entirely on the positions of the planets at the time of each encounter. It assumes that the spacecraft carries enough propellant and power for the entire journey, which is a significant engineering challenge. And it assumes that the spacecraft remains functional for the entire duration, which is far from guaranteed. Spacecraft components degrade over time. Electronics are exposed to radiation. Mechanical parts wear. Propellant can leak. Power systems decay. Voyager 1 and Voyager 2, launched in 1977, are still operational as of the early 2020s, more than 45 years after launch, but they have far exceeded their original design lifetimes, and their systems are gradually failing. Maintaining a spacecraft for decades requires careful design, redundancy, and a degree of luck. Furthermore, the mission as described assumes flybys only, brief encounters during which the spacecraft passes the planet at high speed, collects data for a few hours or days, and then continues on its trajectory. Flybys provide limited data compared to orbital missions. An orbiter can study a planet for months or years, observing changes over time, mapping the entire surface, and conducting repeated observations of specific features. A lander or rover can study surface composition, geology, and potentially search for signs of life. A mission that truly visits every planet, in the sense of comprehensive exploration, would require entering orbit around each planet and possibly deploying landers or probes. This would multiply the mission duration manyfold. Entering orbit requires a significant delta-V burn to slow down and be captured by the planet's gravity. For example, entering orbit around Jupiter requires a delta-V of approximately 2 kilometers per second or more, depending on the desired orbit. Entering orbit around Neptune requires a similar or greater delta-V. Each of these burns consumes propellant. A spacecraft attempting to enter orbit around every planet would need to carry an enormous amount of propellant, making the spacecraft so massive that no current launch vehicle could lift it, or would need to refuel somehow, which is not currently possible in deep space. Advanced propulsion technologies, such as nuclear propulsion or solar sails, might reduce the propellant requirements, but these technologies are still under development and have not been proven on missions to the outer planets. Nuclear propulsion, either nuclear thermal or nuclear electric, offers higher specific impulse than chemical propulsion, meaning it can achieve greater delta-V for a given amount of propellant. Nuclear thermal propulsion heats a propellant, typically hydrogen, using a nuclear reactor and expels it through a nozzle, producing thrust. Nuclear electric propulsion uses a nuclear reactor to generate electricity, which powers an electric propulsion system, such as an ion drive. Both types offer significant advantages for long-duration missions, but come with challenges, including regulatory hurdles, the need to safely launch radioactive material, and the complexity of operating a nuclear reactor in space. NASA and other space agencies have been developing nuclear propulsion systems for decades, but as of the early 2020s, no nuclear propulsion system has been used on a planetary mission. Solar sails use the pressure of sunlight to generate thrust. Photons from the sun carry momentum, and when they reflect off a large, reflective sail, they transfer that momentum to the spacecraft. Solar sails require no propellant, making them theoretically capable of unlimited delta-V given enough time. However, the thrust produced by a solar sail is extremely small, and it decreases with the square of the distance from the sun. A solar sail might be effective for missions in the inner solar system, but the distances of the outer planets, sunlight is so weak that solar sails become impractical. The Planetary Society's Light Sail 2 mission, launched in 2019, successfully demonstrated solar sailing in Earth orbit, but scaling this technology to interplanetary missions remains a challenge. Another propulsion concept is the use of laser or microwave beamed energy. A powerful laser on Earth or in space could shine on a sail attached to a spacecraft, providing continuous thrust over long distances. This concept, known as beam propulsion, could in theory accelerate a spacecraft to a significant fraction of the speed of light, but it requires enormous ground-based infrastructure, precise targeting, and sails capable of withstanding intense energy without degrading. The Breakthrough Starshot Initiative, announced in 2016, proposes using ground-based lasers to propel tiny spacecraft to Alpha Centauri at 20% the speed of light, but this technology is speculative and faces immense technical challenges. Even with advanced propulsion, the question of mission duration remains. Let us consider a hypothetical mission using nuclear electric propulsion capable of continuous low thrust. Such a system could gradually accelerate the spacecraft, building up velocity over months or years, and then decelerate when approaching a planet. This allows for faster transit times than Hohmann transfers because the spacecraft is not coasting for most of the journey. It is continuously accelerating. However, even with continuous thrust, the distances involved are so vast that travel times to the outer planets would still be measured in years. A nuclear electric spacecraft might reach Jupiter in 2 years instead of 5, Saturn in 4 years instead of 7, Uranus in 8 years instead of 16, and Neptune in 12 years instead of 30. These are significant improvements, but the total mission duration to visit all planets would still be on the order of 20 to 30 years, assuming optimal alignments and no time spent in orbit. If the mission includes orbital insertions and extended exploration, the duration could easily exceed 50 years. Consider that entering orbit around each planet might require months of observations, followed by trajectory adjustments to leave orbit and proceed to the next planet. Launching probes or landers would require additional time to design, deploy, and collect data. Communication delays increase with distance, making coordination more difficult. At Neptune's distance, a two-way communication exchange takes over 8 hours, meaning that any decision requiring input from Earth is delayed by half a day. Autonomous systems can mitigate this to some extent, but complex decisions, such as adjusting the mission plan in response to unexpected discoveries, still require human oversight, and the delays can be significant. There's also the issue of human versus robotic missions. All missions to other planets thus far have been robotic. Robots can endure long-duration missions, high radiation environments, and the isolation of space without life support requirements. Sending humans to other planets introduces a host of additional challenges, including life support, radiation protection, psychological health, nutrition, medical care, and the need to return the crew to Earth. A human mission to Mars is considered feasible with current or near-future technology, though it would require a mission duration of approximately 2 to 3 years round trip, including time spent on the surface. A human mission to Jupiter or beyond is far more challenging. The radiation environment beyond Earth's magnetosphere is intense. Galactic cosmic rays and solar energetic particles pose significant health risks to astronauts, increasing the likelihood of cancer and causing acute radiation sickness during solar storms. The journey to Mars exposes astronauts to roughly equivalent doses of radiation as living in a high-altitude city for the same duration, manageable but not negligible. A mission to Jupiter, which passes through intense radiation belts, would expose astronauts to far higher doses, potentially lethal without extensive shielding. Shielding adds mass, which increases propellant requirements, which increases mission cost and complexity. Water, polyethylene, and other materials can provide effective shielding, but carrying enough shielding for a multi-year mission is a significant challenge. Human psychology is another factor. Astronauts on the International Space Station experience isolation, confinement, and monotony, but they are only a few hours away from Earth, and they can communicate in real time with mission control and their families. A crew traveling to Mars would experience communication delays increasing from minutes to over 20 minutes one way as the distance grows. A crew traveling to Jupiter or Saturn would experience delays of 40 minutes to over an hour, making real-time conversation impossible. The psychological effects of this isolation, combined with the knowledge that rescue is not possible if something goes wrong, would be profound. Studies of long-duration isolation, such as those conducted in Antarctic research stations and Mars simulation habitats, suggest that crew cohesion, mental health support, and meaningful work are critical to maintaining morale, but the challenges increase with mission duration. Given these factors, a human mission to visit every planet in the solar system is not feasible with current technology. Even a robotic mission faces enormous challenges. So what is a realistic answer to the question of how long it would take to visit every planet? If we define a visit as a close flyby that collects significant scientific data, and if we accept that the mission would use advanced propulsion, such as nuclear electric or optimized chemical propulsion with gravity assists, and if we assume that the planets are reasonably well aligned, a mission could potentially visit all 8 planets in approximately 25 to 40 years. This estimate accounts for travel times between planets, the time required for gravity assists, and minimal time spent at each planet for data collection. If the planets are not well aligned, the mission could take significantly longer, potentially 50 to 70 years or more, as the spacecraft waits in orbit or executes additional maneuvers to reach the next target. If we define a visit as entering orbit and conducting extended observations, the mission duration would increase substantially. Spending even 1 year in orbit around each planet would add 8 years to the mission, and this is conservative. Missions like Cassini spent over a decade at Saturn. A comprehensive orbital tour of every planet could take 70 to 100 years or more. Such a mission would likely outlast the working lifetimes of the engineers and scientists who designed it, and possibly their entire careers. It would require multi-generational planning, long-term funding commitments, and spacecraft designed for extreme longevity. Another consideration is the order in which planets are visited. The hypothetical mission described earlier visited planets in order of their distance from the Sun, moving from inner to outer planets. However, this order is not necessarily optimal from a mission design perspective. Gravity assists work best when the spacecraft passes a planet at high relative velocity, gaining maximum momentum change. A trajectory that visits inner planets first and then moves outward might not take full advantage of gravity assists. An alternative approach would be to use Earth's gravity to boost the spacecraft outward toward Jupiter, use Jupiter's gravity to redirect towards Saturn, and so forth, visiting outer planets first, and then using a final gravity assist to dive back toward the inner solar system. This approach is similar to what Voyager 2 did, and it could reduce overall mission time, but it depends critically on planetary alignments. The Voyager missions were launched during a rare alignment that will not occur again for more than a century. Without such an alignment, a grand tour of the outer planets alone would take significantly longer. A mission attempting to visit all 8 planets would need to either wait for a favorable alignment, accept a much longer mission duration, or use large amounts of propellant to force trajectories that do not rely on gravity assists. Each of these options has drawbacks. Waiting for an alignment could delay the mission by decades. Accepting a longer mission increases the risk of spacecraft failure and the cost of maintaining mission operations. Using more propellant increases launch mass and cost. Cost is itself a major factor. The Voyager missions cost approximately $865 million in total, equivalent to several billion dollars today when adjusted for inflation. The Cassini mission cost approximately $3.26 billion over its entire lifetime, including development, launch, and operations. A mission visiting all 8 planets would likely cost tens of billions of dollars, if not more, making it one of the most expensive scientific endeavors ever undertaken. Securing funding for such a mission would require international cooperation and sustained political will over decades, neither of which is guaranteed. Space agencies operate on budgets allocated by governments, and those budgets are subject to political priorities, economic conditions, and public interest. A mission that takes 50 years to complete would span multiple generations of politicians, administrators, and taxpayers, all of whom must see value in continuing to fund it. There is also the question of what such a mission would achieve. Each planet offers unique scientific insights. Mercury's proximity to the Sun makes it an ideal laboratory for studying solar interactions and planetary formation in high-temperature environments. Venus provides a cautionary tale of runaway greenhouse effects and atmospheric evolution. Mars holds clues to the history of water and the potential for past or present life. Jupiter's immense size and powerful magnetosphere make it a miniature solar system unto itself, and its moons, particularly Europa and Ganymede, may harbor subsurface oceans. Saturn's rings are the most spectacular in the solar system, and its moon Titan has lakes and rivers of liquid methane, the only other place in the solar system besides Earth with stable surface liquids. Uranus and Neptune, the ice giants, have been visited only once and remain largely mysterious, with unusual magnetic fields and atmospheric compositions. Each planet justifies a dedicated mission on its own merits. A single mission visiting all planets would necessarily provide less detailed data about each than a series of dedicated missions. This trade-off between breadth and depth is inherent in mission design. A grand tour provides a comprehensive overview, but sacrifices the detailed, long-term observations that dedicated missions enable. Given limited budgets, space agencies must choose between these approaches. Historically, the trend has been toward dedicated missions, with each planet receiving one or more specialized spacecraft over time. This approach allows for incremental advances in technology and understanding, with each mission building on the results of previous ones. A grand tour mission would represent a different philosophy, prioritizing a complete survey over detailed study. Nonetheless, the question remains compelling. What would it take to actually do this? Let us construct a more detailed scenario, specifying technology, trajectory, and timeline. Assume a spacecraft is launched in the year 2030 from Earth using a heavy-lift launch vehicle, such as NASA's Space Launch System or SpaceX's Starship. The spacecraft is equipped with nuclear electric propulsion powered by a small nuclear reactor, providing continuous low thrust over the entire mission. It carries an advanced communication system capable of transmitting data at high rates even from the outer solar system, an AI-based autonomous control system to manage operations and respond to anomalies, and a suite of scientific instruments including cameras, spectrometers, magnetometers, and particle detectors. The spacecraft is designed to operate for 50 years, with redundant systems and components rated for extended radiation exposure. The mission plan is as follows. The spacecraft launches from Earth and performs a gravity assist flyby of Earth to gain velocity, a common technique known as an Earth gravity assist, or EGA. It then travels inward toward Venus, reaching it approximately 4 months after launch. A gravity assist at Venus redirects the spacecraft toward Mercury, which it reaches 6 months later, approximately 10 months after launch. The Mercury flyby occurs at high speed, with the spacecraft collecting data for 12 hours as it passes within a few hundred kilometers of the surface. After Mercury, the spacecraft uses its nuclear electric propulsion to adjust its trajectory and returns to Venus, reaching it again approximately 8 months later, 18 months after launch. A second Venus flyby provides another gravity assist, redirecting the spacecraft outward toward Mars. The trajectory from Venus to Mars takes approximately 14 months, bringing the mission elapsed time to 32 months, or roughly 2.7 years. The Mars flyby occurs at a relatively low velocity, allowing the spacecraft to collect data for 24 hours as it passes over the Martian surface and moons. After Mars, the spacecraft fires its propulsion system to begin the long journey to Jupiter. Using continuous thrust, it gradually accelerates over the next 3 years, reaching Jupiter approximately 6 years after launch. During the Jupiter encounter, the spacecraft passes close to the planet, flying through its magnetosphere and observing its cloud bands and storms. It also conducts flybys of the Galilean moons, passing within a few thousand kilometers of Io, Europa, Ganymede, and Callisto over the course of several weeks. This extended encounter at Jupiter lasts approximately 2 months before the spacecraft uses a final gravity assist to redirect towards Saturn. The journey from Jupiter to Saturn takes approximately 4 years, even with continuous thrust, due to the vast distance. The spacecraft reaches Saturn approximately 12 years after launch. At Saturn, it conducts a similar extended encounter, flying past the planet and its rings, and conducting flybys of several of its moons, including Titan, Enceladus, and Mimas. The Saturn encounter lasts approximately 2 months. After Saturn, the spacecraft uses a gravity assist to redirect toward Uranus, beginning another long journey. The trip from Saturn to Uranus takes approximately 6 years, with continuous thrust, bringing the mission elapsed time to approximately 20 years after launch. The Uranus encounter includes flybys of the planet and several of its moons, and observations of its unusual tilted orientation. The Uranus encounter lasts approximately 1 month. Finally, the spacecraft uses a gravity assist from Uranus to redirect toward Neptune. The journey from Uranus to Neptune takes approximately 5 years, bringing the total mission time to approximately 26 years after launch. The Neptune encounter includes flybys of the planet and its moon Triton, with observations of Neptune's atmosphere and magnetic field. The Neptune encounter lasts approximately 1 month. After Neptune, the mission could be considered complete in terms of visiting all 8 major planets. However, the spacecraft is still functional and has propellant remaining. Mission planners might choose to extend the mission to visit objects in the Kuiper Belt, the region beyond Neptune filled with icy bodies and dwarf planets, such as Pluto, Haumea, and Makemake. A trajectory to Pluto from Neptune would take several additional years, potentially extending the mission to 30 years or more. Alternatively, the spacecraft could be directed to study interstellar space, following in the path of Voyager 1 and Voyager 2, which cross the heliopause, the boundary where the solar wind gives way to the interstellar medium. This scenario, while speculative, is grounded in realistic assumptions about propulsion, trajectory, and mission design. 26 years to visit all 8 major planets is achievable with technology that is either currently available or under active development. However, this timeline assumes that everything goes according to plan, that the spacecraft remains functional, that no major anomalies occur, and that funding and support continue throughout the mission. Any one of these assumptions could fail, extending the mission or causing it to be terminated early. History provides cautionary examples. The Mars Observer spacecraft, launched in 1992, was lost just before entering orbit around Mars due to a suspected fuel tank rupture. The mission, which had cost nearly $1 billion, ended in failure. The Galileo spacecraft, launched in 1989, experienced a failure of its high-gain antenna, reducing its data transmission rate by a factor of 100. Engineers compensated by developing advanced data compression techniques, but the mission was severely impacted. The Cassini spacecraft, while ultimately successful, experienced numerous minor anomalies over its 13 years in orbit around Saturn, any one of which could have ended the mission if not for the skill and dedication of the operations team. A mission lasting 26 years or more would face orders of magnitude more opportunities for failure. Redundancy can mitigate some risks. Critical systems can be duplicated so that if one fails, a backup takes over. The Voyager spacecraft have redundant computers, transmitters, and other components, which is part of why they have lasted so long. However, redundancy adds mass and complexity, and not everything can be redundantly. If the primary propulsion system fails, a backup may not exist because carrying 2 complete propulsion systems would be prohibitively heavy. If the nuclear reactor fails, there may be no backup power source capable of sustaining the spacecraft. If the spacecraft structure is damaged by a micrometeorite impact, there is no repair mechanism. Spacecraft are designed to be as robust as possible, but they are not invincible. Another risk is obsolescence. Technology advances rapidly, and a spacecraft designed in the year 2030 might seem primitive by the time it reaches Neptune in 2056. Communication protocols, data formats, and ground station equipment all evolve. The Deep Space Network, NASA's array of large radio antennas used to communicate with spacecraft, must be maintained and upgraded to support missions over decades. If the technology used by the spacecraft becomes obsolete, it may become difficult or expensive to communicate with it. This has not yet been a major issue for long-duration missions, but it is a consideration for missions lasting half a century or more. There is also the question of what constitutes a visit. The scenario described involves flybys of each planet, with data collection occurring over hours, days, or weeks as the spacecraft passes. This is the minimum definition of a visit. A more ambitious definition would involve entering orbit around each planet, conducting months or years of observations, and possibly deploying landers or atmospheric probes. Such a mission would be far more scientifically valuable, but would require a fundamentally different design. An orbiter must carry enough propellant to slow down and be captured by each planet's gravity, then later accelerate to leave orbit and continue to the next planet. The delta-v requirements for this are staggering. Consider the delta-v needed to enter and leave orbit around each planet. For Mercury, entering orbit requires approximately 1.5 kilometers per second, and leaving orbit requires a similar amount, totaling 3 kilometers per second. For Venus, the values are higher due to its larger mass, approximately 4 kilometers per second total. For Mars, approximately 2.5 kilometers per second total. For Jupiter, entering and leaving orbit could require 10 kilometers per second or more, depending on the orbit. For Saturn, Uranus, and Neptune, similar or higher values. Adding these up, the total delta-v requirement for entering and leaving orbit around all 8 planets could exceed 50 kilometers per second. No current propulsion system can provide this much delta-v to a spacecraft of meaningful size. Nuclear electropropulsion, with its high specific impulse, could potentially achieve this, but the mission duration would extend dramatically. Ion drives produce very low thrust, meaning that the time required to accelerate and decelerate is long. Entering orbit around Jupiter using an ion drive might take months of continuous thrusting. Leaving orbit and accelerating towards Saturn might take another few months. Across 8 planets, the time spent thrusting into and out of orbits could add years to the mission. A realistic estimate for a mission that enters orbit around each planet might be 50 to 70 years or even longer. At this point, we must confront the reality that such a mission is beyond the capabilities of current or near-term technology if it is to be completed within a human lifetime. However, if we relax the constraint of a single spacecraft and instead consider a coordinated campaign of multiple spacecraft, each dedicated to a subset of planets, the problem becomes more tractable. One spacecraft could visit the inner planets, Mercury, Venus, and Mars, completing its mission in approximately 5 years. Another spacecraft could visit the outer planets, Jupiter, Saturn, Uranus, and Neptune, completing its mission in approximately 25 years. Both missions could be launched within a few years of each other, and while the second mission would take far longer, the overall campaign would provide comprehensive coverage of all planets within the time frame of the longer mission. This approach is essentially what has been happening over the past several decades. Numerous missions have visited Mars, including orbiters, landers, and rovers. Missions have visited Venus, Mercury, Jupiter, and Saturn. Uranus and Neptune have been visited only once, by Voyager 2, and there are proposals for future missions to return to these ice giants. If these proposals are realized, the solar system will have been comprehensively explored by a fleet of spacecraft, each optimized for its target, within a time frame spanning several decades. This distributed approach has the advantage of flexibility, allowing each mission to use the best available technology at the time of launch and reducing the risk that a single failure will cause the loss of the entire campaign. Yet the original question asks about a single journey, one continuous mission visiting every planet. This is a different challenge, one that captures the imagination because it echoes the concept of a grand voyage, an odyssey through the solar system. Such a mission would be a statement of capability and ambition, a demonstration that humanity can reach every corner of its cosmic neighborhood. It would also be a scientific treasure, providing a consistent dataset collected by a single set of instruments, allowing for direct comparisons between planets without the uncertainties that arise when data is collected by different spacecraft with different instruments and calibrations. To make such a mission feasible, we might need to invoke technologies that are currently speculative but theoretically possible. One such technology is in situ resource utilization, or ISRU, the concept of using resources found in space to support missions. For example, water ice exists on the Moon, Mars, and potentially on asteroids and the moons of Jupiter and Saturn. Water can be split into hydrogen and oxygen, which can be used as rocket propellant. A spacecraft that could refuel at multiple locations along its journey would not need to carry all of its propellant from Earth, reducing launch mass and increasing mission flexibility. However, ISRU technology is still in early stages of development, and deploying the infrastructure needed to extract and process resources on other worlds would itself require significant missions and investments. Another speculative technology is fusion propulsion. Fusion reactors generate energy by fusing light atomic nuclei, such as hydrogen isotopes, into heavier nuclei, releasing large amounts of energy in the process. A fusion rocket could provide both high thrust and high specific impulse, enabling fast transit times and large delta-v without requiring enormous amounts of propellant. Fusion propulsion has been studied for decades, and while progress has been made in achieving controlled fusion reactions in laboratory settings, a working fusion rocket remains decades away from reality. If fusion propulsion becomes available, it could revolutionize interplanetary travel, reducing travel times to the outer planets from years to months. Antimatter propulsion is even more speculative. When matter and antimatter meet, they annihilate, converting their entire mass into energy according to Einstein's equation E equals mc squared. The energy density of antimatter is unmatched by any other fuel source. A spacecraft using antimatter propulsion could achieve extremely high velocities, potentially enabling travel to the outer planets in weeks rather than years. However, antimatter is extraordinarily difficult to produce and even more difficult to store. Current production rates are measured in nanograms per year, and the cost is prohibitive. Antimatter propulsion remains firmly in the realm of theoretical research, with no practical implementation expected in the foreseeable future. Returning to realistic technologies, we can consider missions that prioritize speed over comprehensive exploration. A spacecraft designed purely for fast transit, using a powerful launch vehicle and optimized trajectories, could visit each planet on a flyby basis in a shorter time frame. The New Horizons mission, launched in 2006, reached Pluto in 9.5 years, traveling faster than any previous spacecraft. New Horizons achieved this speed by using a large launch vehicle, the Atlas V, and a gravity assist from Jupiter. If a similar approach were applied to a Grand Tour mission, using a powerful launch vehicle, multiple gravity assists, and minimal time at each planet, it might be possible to visit all 8 planets in 15 to 20 years. This would be the fastest realistic scenario, though it would sacrifice scientific return for speed. Speed has its costs. High-velocity flybys reduce the time available for data collection. A spacecraft passing a planet at tens of kilometers per second has only a brief window, sometimes just hours, during which the planet is close enough for detailed observations. Instruments must be carefully targeted, and data must be collected and stored rapidly. Communication bandwidth limits how much data can be transmitted back to Earth, especially from the outer planets where signal strength is weak. Compressing mission duration by increasing velocity is a trade-off that must be carefully evaluated against scientific goals. Communication itself is a challenge that worsens with distance. The strength of a radio signal decreases with the square of the distance from its source. A spacecraft at Jupiter, 5 AU from Earth, receives sunlight and transmits signals that are 25 times weaker than at Earth. A spacecraft at Neptune, 30 AU from Earth, receives sunlight and transmits signals that are 900 times weaker. Ground stations must have large antennas and sensitive receivers to detect these faint signals. The Deep Space Network uses antennas 70 meters in diameter, among the largest in the world, to communicate with distant spacecraft. Even with these enormous antennas, data rates from the outer planets are slow. New Horizons, during its Pluto flyby, transmitted data at approximately 1 kilobit per second, slower than the dial-up internet of the 1990s. At that rate, transmitting a single high-resolution image can take hours. Data storage and compression are critical. Spacecraft carry onboard storage, typically solid-state memory, to record data when transmission is not possible or when data is being collected faster than it can be transmitted. Compression algorithms reduce the size of data files, allowing more information to be stored and transmitted. However, compression is lossy for some types of data, meaning that some information is discarded to achieve smaller file sizes. Mission planners must balance the desire for high-resolution, uncompressed data with the practical constraints of storage and transmission. The scientific instruments themselves must be chosen carefully. A spacecraft visiting every planet must carry instruments versatile enough to study a wide range of environments, from the scorching heat of Mercury to the cryogenic cold of Neptune, from the thin atmosphere of Mars to the thick atmosphere of Venus, from the rocky surfaces of the inner planets to the gaseous and icy compositions of the outer planets. Some instruments, such as cameras and spectrometers, are broadly applicable. Others, such as seismometers or drills, are specific to surface missions and not relevant for flybys. The mass and power budgets of the spacecraft limit how many instruments can be carried, forcing mission planners to prioritize. Mass and power are the two fundamental constraints on spacecraft design. Every kilogram of mass requires propellant to accelerate it, and propellant itself has mass, creating a feedback loop captured by the rocket equation. Power is needed to operate instruments, communication systems, computers, and thermal control. Solar panels provide power in the inner solar system, but their effectiveness drops sharply with distance from the sun. Beyond Mars, solar panels become impractical, and spacecraft rely on RTGs or potentially nuclear reactors. RTGs degrade over time as the plutonium decays, reducing power output. A spacecraft designed for a 50-year mission must carry enough power capacity to operate its systems even after decades of decay, or it must be designed to shed non-essential systems as power becomes scarce. Thermal control is another challenge. In the inner solar system, spacecraft must dissipate heat to avoid overheating. Radiators, sunshades, and reflective coatings are used to manage temperature. In the outer solar system, the problem reverses. Spacecraft must retain heat to keep instruments and electronics from freezing. RTGs provide waste heat that can be used to warm the spacecraft, and heaters powered by the spacecraft's electrical system can maintain critical temperatures. However, as power declines, heating capacity declines, and eventually, some systems may fail due to cold. Voyager 2's primary radio transmitter operates in a temperature range that is carefully managed by heaters. If those heaters fail, the transmitter could freeze and stop working, ending the mission. Radiation is a pervasive hazard. Galactic cosmic rays are high-energy particles originating from outside the solar system, and they constantly bombard spacecraft. Solar energetic particles are bursts of particles from the sun, particularly during solar storms. Both types of radiation can damage electronics, causing bit flips in computer memory, degradation of solar panels, and eventual failure of components. Radiation hardening, the process of designing electronics to withstand radiation, is standard for space missions, but it is imperfect. Over time, accumulated radiation damage can cause systems to fail. Jupiter's intense radiation belts are particularly hazardous, and any spacecraft passing close to Jupiter must be designed to survive the dose. Micrometeorites, tiny particles of dust and rock traveling at high speeds, pose another risk. Impacts can damage solar panels, antennas, and other exposed surfaces. While most micrometeorites are small and cause only minor damage, a large enough impact could puncture a fuel tank or disable a critical component. Spacecraft are designed with some level of shielding, but there is always a residual risk. Over a mission lasting decades, the cumulative probability of a damaging impact increases. Navigation in deep space is a subtle challenge. Spacecraft positions are determined by tracking radio signals from Earth and measuring their Doppler shift, which indicates the spacecraft's velocity relative to Earth, and the time delay, which indicates distance. These measurements are combined with knowledge of the spacecraft's trajectory and the gravitational influences of the Sun and planets to calculate its position. However, these calculations are not perfect. Small errors in position accumulate over time, and trajectory corrections are necessary. Each correction requires firing thrusters, which consumes propellant. A mission lasting decades requires numerous corrections, and the propellant budget must account for this. Gravity is not uniform. The sun's gravity dominates the solar system, but the planets also exert gravitational forces, and these forces perturb spacecraft trajectories. The orbits of the planets themselves are not perfect ellipses. They're perturbed by the gravitational interactions of the planets with each other, an effect captured by celestial mechanics and described by the in-body problem. For most purposes, these perturbations are small and can be calculated and accounted for, but over long timescales and large distances, they accumulate and must be factored into mission planning. Einstein's theory of general relativity introduces additional small effects. While Newtonian gravity is sufficient for most spacecraft navigation, general relativity predicts that gravity affects the passage of time and the path of light, and these effects, though tiny, are measurable. The Cassini mission tested general relativity by measuring the Doppler shift of radio signals passing close to the Sun, where relativistic effects are most pronounced. For a mission to the outer planets, relativistic corrections to navigation are negligible, but they are not zero, and for the highest precision, they must be included. We must also consider the human element, the engineers and scientists who design, build, and operate the spacecraft. A mission lasting 26 years, or 50 years, or longer, will outlast the careers of many of the people who work on it. The team that launches the spacecraft will not be the same team that receives the final data. Knowledge must be passed down, documentation must be maintained, and institutional memory must be preserved. This is a challenge faced by all long-duration missions. NASA has processes in place to manage this, including detailed documentation, training programs, and overlap between generations of team members, but it is never seamless. People retire, change careers, or pass away, and their expertise goes with them unless it has been captured and transferred. Funding continuity is perhaps the most uncertain factor. Space missions are funded by government agencies, which are subject to changing priorities. A mission launched during a period of strong political support for space exploration might find itself struggling for funding years later if priorities shift. The James Webb Space Telescope, launched in 2021, faced numerous funding crises and schedule delays over its decades-long development. The mission was nearly canceled multiple times, but survived due to advocacy by the scientific community and space policy stakeholders. A Grand Tour mission would face similar risks, and maintaining funding over a multi-decade timeline would require sustained effort. International cooperation could help. The International Space Station is a collaborative project involving NASA, the Russian Space Agency Roscosmos, the European Space Agency, the Japanese Space Agency JAXA, and the Canadian Space Agency. This cooperation has enabled the station to remain continuously occupied for over 2 decades. A Grand Tour mission could similarly involve multiple space agencies, sharing costs, expertise, and data. The European Space Agency contributed the Huygens probe to the Cassini mission, which landed on Titan in 2005. Similar collaborations could enhance a Grand Tour mission, but they also introduce complexity, as the agencies must coordinate their efforts and reconcile different priorities and technical standards. Commercial spaceflight is another factor. Companies like SpaceX, Blue Origin, and others are developing launch vehicles and spacecraft with the goal of reducing costs and increasing access to space. If launch costs continue to decline, missions that were once prohibitively expensive might become feasible. SpaceX's Starship, currently under development, is designed to be fully reusable and capable of carrying large payloads to orbit and beyond. If Starship succeeds, it could enable missions to the outer planets that would have been impossible with previous launch vehicles. However, commercial spaceflight is still maturing, and it is unclear how much costs will ultimately decrease or whether commercial companies will be interested in funding or conducting deep space missions, which offer no immediate economic return. Scientific return is ultimately the justification for any space mission. What we learn from a grand tour that visits every planet. Each planet offers unique insights. Mercury's surface is heavily cratered, resembling the Moon, but it also has unusual features such as scarps, cliffs that formed as the planet's interior cooled and contracted. Studying Mercury helps us understand planetary formation and the effects of proximity to the Sun. Venus, despite being similar in size to Earth, underwent a runaway greenhouse effect that turned it into a hellish world. Understanding why Venus and Earth evolved so differently is crucial for understanding planetary climates and the potential habitability of exoplanets. Mars once had liquid water on its surface, and it may have been habitable in the past. Finding evidence of past or present life on Mars would be one of the most important discoveries in science. Jupiter's moons are worlds unto themselves. Europa has a subsurface ocean beneath its icy crust, and hydrothermal activity on the ocean floor could provide energy for life. Ganymede is the largest moon in the solar system and has its own magnetic field. Callisto is heavily cratered, a record of impacts over billions of years. Io is the most volcanically active body in the solar system, its surface constantly resurfaced by lava flows. Saturn's moon Titan has a thick atmosphere and lakes of liquid methane and ethane, the only other place in the solar system with stable surface liquids. Enceladus has geysers that erupt from cracks in its icy surface, spraying water ice into space, evidence of a subsurface ocean. These moons are prime targets in the search for life beyond Earth. Uranus and Neptune, the ice giants, are poorly understood. Their interiors are composed of water, methane, and ammonia ices under extreme pressure, possibly forming exotic states of matter. Their magnetic fields are tilted and offset from their centers, unlike any other planet. Their atmospheres contain methane, which gives them their blue color, and they have storms and winds despite being so far from the Sun. Studying these planets helps us understand planetary formation and the diversity of worlds. Many exoplanets discovered around other stars are similar in size to Uranus and Neptune, making them important analogs for understanding those distant worlds. A grand tour would provide a comprehensive dataset collected by a single spacecraft with a consistent set of instruments, allowing direct comparisons between planets. This is valuable because it eliminates some of the uncertainties that arise when data is collected by different spacecraft. For example, if two different cameras on two different spacecraft measure the color of two planets, differences in the camera's calibration could lead to differences in the measured colors that do not reflect real differences between the planets. Using a single spacecraft with a single camera eliminates this source of uncertainty. However, the trade-off is that a single spacecraft cannot carry as many instruments or spend as much time at each planet as dedicated missions. A dedicated mission to Europa, for example, could carry instruments specifically designed to study that moon, such as ice-penetrating radar to probe the thickness of the ice crust, or a lander to sample the surface. A Grand Tour spacecraft, constrained by mass and power, could not carry such specialized instruments. The scientific return from a Grand Tour would be broad, but not deep. Given these considerations, the answer to how long it would take to visit every planet in the solar system depends on what we mean by visit and what technology we use. For a flyby mission using current or near-term technology, with optimized trajectories and gravity assists, a realistic estimate is 25 to 40 years. This assumes favorable planetary alignments, no major spacecraft failures, and minimal time at each planet. If we define a visit as entering orbit and conducting extended observations, the mission duration could exceed 50 to 100 years and would require propulsion technology beyond what is currently available. If we relax the requirement of a single spacecraft and instead consider a coordinated campaign of multiple spacecraft, each dedicated to a subset of planets, the time required is determined by the longest individual mission, which would still be on the order of 25 to 30 years for a mission to the outer planets. The fundamental constraints are distance, velocity, energy, and time. The distances between planets are vast, and traversing them at velocities achievable with chemical rockets takes years. Gravity assists can reduce travel time, but depend on planetary alignments that occur infrequently. Advanced propulsion, such as nuclear electric or fusion rockets, could reduce travel times, but these technologies are not yet ready. Energy is required to accelerate and decelerate, and that energy must come from propellant or from external sources, such as sunlight or beam power. Time is the inescapable dimension, the medium through which all journeys occur. And in space, time is measured in years and decades, not hours and days. The solar system is a place of immense scale, and visiting every planet within it is a challenge that pushes the limits of technology and human ambition. It is a challenge that has been partially met by missions like Voyager, which visited multiple outer planets, and which could be fully met by future missions if the necessary investments are made. But it is not a challenge that can be met quickly or easily. It requires patience, persistence, and a willingness to commit resources over timescales that exceed individual careers and even individual lifetimes. There's a philosophical dimension to this question as well. To visit every planet is to complete a survey of our cosmic backyard, to say that we have set foot, however briefly and robotically, on every major world orbiting our sun. It is an act of exploration in the tradition of the great voyages of discovery on Earth, when explorers circumnavigated the globe and mapped unknown continents. But space is not the ocean, and planets are not islands. The challenges are greater, the risks are higher, and the rewards are more abstract. There is no gold to be found on Mercury, no spices on Mars, no trade routes to be established with Jupiter. The rewards are knowledge, understanding, and the satisfaction of curiosity. These are intangible, but they are not insignificant. They are the foundation of science and the fuel of progress. Humanity's expansion into space is often framed in terms of survival. The idea that we must become a multi-planet species to ensure our long-term survival in case of catastrophe on Earth. This is a compelling argument, but it is not the only one. Exploration is also driven by curiosity, the desire to know what is out there, to see what no one has seen, to answer questions that have been asked for centuries. How did the planets form? What is the nature of the solar system? Are we alone? These questions motivate missions to other worlds, and they will continue to motivate them as long as humans exist. The journey to every planet is also a test of our capabilities. Can we build machines that last for decades in the harshest environments imaginable? Can we navigate across billions of kilometers with precision? Can we coordinate efforts across institutions and nations over timescales longer than any single administration or government? The answer is yes, we can, because we have already done these things to a limited extent. But doing them on the scale required for a true grand tour is a step beyond what has been accomplished so far. It requires advances in technology, increases in funding, and sustained commitment. These are not insurmountable obstacles, but they are significant ones. If such a mission were launched today, or in the near future, what would it look like? The spacecraft would be large, on the order of several tons, to accommodate propulsion, power, instruments, and communication systems. It would be launched on a heavy-lift vehicle, possibly requiring multiple launches if the spacecraft is too large for a single launcher. It would carry a nuclear reactor or multiple RTGs for power, providing hundreds of watts to a few kilowatts of electrical power. It would have a large communication antenna, several meters in diameter, to transmit data back to Earth. It would carry a suite of instruments including cameras operating in multiple wavelengths, spectrometers to analyze composition, magnetometers to measure magnetic fields, particle detectors to study charged particles, and possibly radar to probe beneath surfaces. The spacecraft would be controlled by an onboard computer, radiation-hardened and redundant, capable of autonomous operation. It would have thrusters for trajectory corrections and attitude control, using hydrazine or a similar propellant. It would have a main propulsion system, either a chemical engine for impulsive maneuvers or an ion drive for continuous low thrust. It would be covered in thermal insulation and heaters to maintain temperature. It would have antennas for receiving commands from Earth and transmitting data back. It would have solar panels if operating in the inner solar system or rely entirely on nuclear power if designed for the outer planets. The launch would be timed to take advantage of planetary alignments, with a trajectory planned years in advance. After launch, the spacecraft would enter a coast phase, during which it travels along its initial trajectory with minimal course corrections. As it approaches the first planet, Venus or Mercury, the operations team would begin preparing for the encounter, uploading command sequences, calibrating instruments, and monitoring the spacecraft's health. The encounter itself would be a period of intense activity, with instruments collecting data as rapidly as possible and storing it on board for later transmission. After the encounter, the spacecraft would resume coasting toward the next planet, and the process would repeat. Over the course of the mission, the operations team would face numerous challenges. Systems would fail, and workarounds would need to be developed. Instruments would degrade, and calibration procedures would need to be adjusted. Communication would become more difficult as distance increased, and data rates would drop. Power output would decline, and non-essential systems would be turned off to conserve energy. Despite all of this, the mission would continue, driven by the dedication of the people operating it and the value of the data being collected. Eventually, after 2 or 3 or more decades, the spacecraft would complete its encounters with all 8 planets. It would transmit the last of its data back to Earth, and then, if it is still functional, it would continue outward, joining Voyager 1 and Voyager 2 in interstellar space. It would carry with it a record of its journey, encoded in its memory and in the images and measurements it collected, a testament to the ingenuity and determination of the species that built it. But until such a mission is flown, the question remains hypothetical. How long would it take? The answer is 26 years at a minimum for a fast flyby mission with favorable conditions. 50 years or more for a comprehensive mission with orbital insertions. Perhaps a century or longer if we wait for the perfect alignment and attempt to minimize propellant use. The exact number depends on countless factors, many of which are beyond our control. But the fundamental truth is that it takes a long time, longer than most people live, longer than careers, longer than political administrations. It takes commitment across generations, a willingness to start something that others will finish, to plant trees under whose shade we will never sit. And yet we do it. We launch spacecraft that will operate for decades, knowing that we will not live to see their final transmissions. We plan missions that will be completed by people who have not yet been born. We do this because the pursuit of knowledge is a fundamental human drive, because we are curious, because we want to know, and because, in the end, the question of how long it takes is less important than the fact that we try. The physics of orbital mechanics does not care about human lifespans or political will. It operates according to laws that were set in place billions of years ago when the solar system formed. The planets orbit the sun in ellipses, moving at speeds determined by their distance for the gravitational center. The time it takes to travel between them is determined by these orbits, by the energy available to change velocity, and by the clever use of gravity assists to steal momentum from the planets themselves. These are the rules, and they cannot be changed. We can only work within them, optimizing trajectories, advancing propulsion, and building spacecraft that can endure the journey. The history of space exploration is a history of incremental progress. The first artificial satellite, Sputnik, was launched in 1957. The first human in space, Yuri Gagarin, flew in 1961. The first humans on the moon, Neil Armstrong and Buzz Aldrin, walked there in 1969. The first spacecraft to leave the solar system, Voyager 1, crossed the heliopause in 2012, 35 years after launch. Each of these milestones seemed impossible until it was achieved. A mission to visit every planet would be another such milestone, a capstone to the age of planetary exploration. But achieving it requires more than technology. It requires vision, the ability to imagine a future in which such a mission is not only possible but necessary. It requires leadership, people willing to advocate for long-term investments in science and exploration. It requires education, training the next generation of engineers and scientists who will design and operate these missions. It requires public support, a society that values exploration and is willing to allocate resources to it. And it requires luck, that the spacecraft does not fail, that funding does not dry up, that the mission is allowed to continue to completion. None of these factors is guaranteed, but all of them are achievable. We have the technology, or can develop it. We have the knowledge. We have the desire. What we need is the will to commit, to say that visiting every planet is important enough to dedicate the time and resources required. If we make that commitment, then the answer to how long it would take is clear: 2 or 3 or 4 decades, depending on the details. If we do not make that commitment, then the answer is never, because the mission will never be flown. So the question is not just a technical one. It is a question about us, about our priorities, about what we value. Do we value knowledge enough to wait decades for answers? Do we value exploration enough to invest in missions that will not pay off within the next budget cycle? Do we value the future enough to start projects that we will not live to see completed? These are the real questions underlying the technical challenge of visiting every planet. And the answers to these questions will determine whether the mission is ever attempted and whether it succeeds. The universe is vast, and the solar system, our tiny corner of it, is already almost incomprehensibly large. The distances between planets are measured in tens of millions or hundreds of millions of kilometers. The time it takes to cross these distances is measured in months and years and decades. To visit every planet is to confront this scale directly, to accept that space is not a place for instant gratification or quick results. It is a place that demands patience, where progress is slow and hard-won, where success is the result of careful planning, robust engineering, and persistent effort over long timescales. This is the reality of space exploration. It is not the space travel of science fiction, where ships jump to hyperspace and cross the galaxy in moments. It is the space travel of reality, where every kilometer must be earned through propellant or gravity, where every bit of data must be transmitted across billions of kilometers of empty space, where every system must be designed to last for decades in an environment that is hostile in every way. It is difficult, expensive, and slow. But it is also possible, and it is being done incrementally, mission by mission, year by year. In the time it takes to visit every planet, a child could be born, grow up, graduate from university, start a career, and perhaps even begin to raise a family of their own. In the time it takes, governments will rise and fall, technologies will be invented and become obsolete, wars will be fought, and peace treaties signed. The world will change in countless ways, but the mission will continue, a constant thread running through the decades, a testament to the long view, to the idea that some goals are worth pursuing even if we will not live to see their completion. And when a mission is complete, when the data has been transmitted and analyzed, when the images of every planet have been published and studied, what will we have gained? We will have a comprehensive understanding of our solar system, a complete survey of the worlds that orbit our sun. We will have answered questions about planetary formation, atmospheric evolution, magnetic fields, and the potential for life beyond Earth. We will have pushed the boundaries of our technology and our capabilities. And we will have demonstrated to ourselves and to future generations that we are a species capable of long-term thinking, of planning and executing projects that span generations, of looking beyond the immediate and seeing the distant horizon. This is the value of a grand tour. It is not just the science, though the science is invaluable. It is not just the technology, though the technological advances are significant. It is the statement it makes, the message it sends, that we are explorers, that we do not stop at the first obstacle or the first planet, that we're driven to see what is over the next hill, around the next orbit, at the edge of our solar system and beyond. This drive is part of what makes us human, and satisfying it requires accepting the timescales imposed by physics and the constraints of reality. So when we ask how long it would take to visit every planet in the solar system, we are asking a question that has a technical answer, measured in years and decades, but also a deeper answer, measured in commitment and will. The technical answer is that it would take at least 25 to 40 years for a flyby mission, and 50 to 100 years or more for an orbital mission, depending on the technology used and the alignments of the planets. The deeper answer is that it would take as long as we are willing to wait, as long as we are willing to work, as long as we are willing to dedicate the resources and effort required. If we are willing, then it is achievable. If we are not, then it remains a dream, a tantalizing possibility that we never quite reach. But the fact that we can even contemplate such a mission, that we can calculate trajectories and design spacecraft and estimate timelines, is itself remarkable. A century ago, space travel was pure fantasy, the stuff of novels and speculation. 50 years ago, we had just begun to send probes to other planets, tentative first steps into the solar system. Today, we have visited every planet with robotic spacecraft, flown past Pluto, and sent probes into interstellar space. The progress has been extraordinary, and there is no reason to think it will stop. The mission to visit every planet in a single journey is the next logical step, a natural extension of what we have already done. And perhaps, someday, it will not be a robotic spacecraft making this journey, but humans. A crewed mission to every planet is far more challenging than a robotic one, requiring life support, radiation shielding, psychological support, and the ability to return the crew to Earth. Such a mission is beyond current technology, but it is not beyond imagination. If propulsion technology advances sufficiently, if closed-loop life support systems are perfected, if radiation shielding becomes lightweight and effective, then a crewed grand tour might become feasible. It would be the ultimate voyage, a journey that takes decades and carries a crew across the entire breadth of the solar system. It would be dangerous, difficult, and expensive, but it would also be the fulfillment of a dream that humans have held for as long as we have looked up at the night sky and wondered what lies beyond. Until then, we rely on our robotic emissaries, the spacecraft we send ahead to explore on our behalf. They are our eyes and ears, extending our senses across distances we cannot physically cross. They carry our curiosity and our questions, and they return to us answers in the form of data, images, and measurements. They are marvels of engineering, capable of surviving for years or decades in environments that would destroy any unprotected human in seconds. They're the product of thousands of people working together, each contributing their expertise, each playing a role in the collective effort to explore the cosmos. A mission to visit every planet would be the greatest of these efforts, a culmination of everything we have learned about spaceflight, a synthesis of propulsion, navigation, communication, power, and autonomy. It would require the best minds, the most advanced technology, and the sustained support of institutions and governments. It would be expensive, but the cost must be measured against the value of what we would learn and against the cost of not exploring, of remaining ignorant of our surroundings, of not pushing the boundaries of what we can achieve. The cost of space missions is often criticized, the argument being that the money could be better spent on problems here on Earth. This is a fair point, and it deserves a thoughtful response. Space exploration does not solve hunger, poverty, or disease directly, but it does contribute to solving these problems indirectly. The technologies developed for space missions have applications on Earth, from satellite communication to medical imaging to material science. The knowledge gained from studying other planets helps us understand Earth better, including its climate, geology, and potential for catastrophic events. And the inspiration provided by space exploration motivates young people to pursue careers in science and engineering, creating the workforce that will solve future challenges. Beyond these practical benefits, space exploration fulfills a fundamental human need to explore, to discover, to understand. This need is part of what makes us human, and satisfying it has value even if the benefits are not immediately tangible. The question of how long it would take to visit every planet is ultimately a question about the nature of exploration itself. Exploration is not a quick process. It requires time to plan, time to build, time to travel, and time to analyze the results. It requires accepting that the journey is as important as the destination, that the process of getting there teaches us as much as what we find when we arrive. It requires patience, persistence, and a willingness to embrace uncertainty. These are not qualities that modern society always values, but they are essential for any endeavor that pushes the limits of what is known and what is possible. In the end, the time it takes to visit every planet is a reflection of the scale of the solar system and the limits of our current technology. It is a long time, measured in decades, but it is not infinite. It is achievable with the right commitment and the right technology. And it is worth doing, not because it is easy, but because it is hard, because it challenges us to think beyond the present moment and to work toward goals that will not be realized in our lifetimes. This is the essence of long-term thinking, and it is the essence of exploration. It is what allows us to reach beyond our grasp, to strive for something greater than ourselves, to contribute to a project that will outlast us and benefit generations to come. The planets are out there, circling the sun, moving through their orbits as they have for billions of years and will for billions more. They do not wait for us. They do not care whether we visit them or not. But we care. We look up at the night sky and see points of light, and we wonder what they are made of, whether they could support life, what it would be like to stand on their surfaces. These questions drive us to build spacecraft and launch them across the vast emptiness of space, to send our creations to places we cannot go ourselves, to learn everything we can about these distant worlds. And so we return to the question, how long would it really take to visit every solar system planet? The answer is not simple, because it depends on definitions and technology and alignments and countless other factors. But if we take the question to mean a realistic mission, using technology that exists or is under development, with flybys of all 8 major planets, using gravity assists and optimized trajectories, with the understanding that the planets must be in favorable positions and the spacecraft must remain functional throughout, then the answer is approximately 25 to 40 years. That is the minimum time frame for a mission that could visit every planet in a single journey. It is a long time, but it is not impossible. It is achievable, and it represents the scale of the challenge we face when we seek to explore the entirety of our solar neighborhood. If we demand more than flybys, if we require orbital insertions and extended observations, then the time frame extends to 50 years or more, and the technological requirements increase beyond what is currently available. If we are willing to accept a distributed campaign of multiple spacecraft rather than a single mission, then the time frame is determined by the longest individual mission, which is still on the order of 25 to 30 years. No matter how we approach the problem, the answer is measured in decades, not years or months. This is the reality of interplanetary travel, and it is a reality that will remain unless and until we develop fundamentally new propulsion technologies that allow us to travel faster. Such technologies are the subject of ongoing research. Fusion propulsion, antimatter propulsion, beamed energy propulsion, and other concepts are being studied, and some of them may eventually become practical. If they do, the travel times to the outer planets could be reduced from years to months, and a mission to visit every planet could be completed in a fraction of the time currently required. But these technologies are not available today, and predicting when or if they will become available is difficult. So we must plan based on what we have, and what we have requires time, patience, and commitment. The journey to every planet is a journey through time as much as it is a journey through space. It is a journey that unfolds over decades, that requires planning and execution by multiple generations, that tests our ability to sustain effort over long periods. It is a journey that demands the best of us, our ingenuity, our perseverance, our vision. And it is a journey that, if we choose to undertake it, will define us as a species, as explorers who do not stop at the first challenge, who do not accept limits, who reach for the stars even knowing that the journey will be long and difficult. The question has been asked, and the answer has been given in all its complexity and nuance. It would take decades to visit every planet, with the exact duration depending on a multitude of factors. This is the reality of space exploration, a field where progress is measured not in days or weeks, but in years and decades, where success is the result of sustained effort over timescales that exceed individual lives. It is a humbling reality, a reminder of how vast the universe is and how small we are within it. But it is also an inspiring reality because it shows us what we are capable of when we commit to long-term goals, when we work together across institutions and generations, when we refuse to be daunted by distance or time. And so the planets continue their eternal dance around the sun, waiting, indifferent to whether we visit them or not. But we are not indifferent. We are driven to know, to explore, to understand. And that drive, more than any technology or trajectory, is what will ultimately determine whether we visit every planet and how long it takes to do so. The answer is in our hands, in our willingness to commit, to invest, to wait. If we choose to do so, then the journey will happen, and the time it takes will be the time required by physics, by orbital mechanics, by the vast distances of space. And when it is complete, we will have achieved something extraordinary, something that speaks to the best of what we are capable of as a species. The silence of space is patient. The planets have been there for billions of years, and they will be there for billions more. Whether we visit them in the next few decades or the next few centuries is, on cosmic timescales, insignificant. But to us, it matters. It matters because we live on human timescales, because we have finite lives and finite time to explore and discover. It matters because the questions we ask now are the questions that will be answered by the missions we launch now. It matters because the decisions we make today will determine what future generations know about the solar system and what they will be capable of achieving. So the question stands, and the answer has been explored from every angle, examined through the lens of physics and engineering and human ambition. How long would it take to visit every planet in the solar system? The technical answer is clear: decades, with the exact number depending on the specifics of the mission. But the deeper answer is that it takes as long as we allow it to take, as long as we are willing to work toward that goal, as long as we keep the vision alive and continue to invest in the technology and the missions that will make it possible. The time required is long, but it is not forever. It is achievable. And that is perhaps the most important answer of all.